going to take a look at the area under a velocity time graph. Remember, a velocity time graph tells us how fast we're going at any given time. So just first looking at this graph, this is a car, let's say, that's at 0 seconds is going 8 meters per second positive, so it's moving forward at 8 meters per second. And if you look all the way up to like 2 seconds, it's still going forward at 8 meters per second. And at 3 seconds, it actually goes from 8 meters per second and suddenly starts going backwards at 4 meters per second. Now that's a little unrealistic. It obviously changes its speed in a very short space of time. So normally we would write this as maybe a dotted line. But let's just keep it really simple. Here's a graph of an object, the VT graph, and we're going to look at the area. Well, this shape here, the area is going to be length times width. So I've got a height here of 8. So the area for this part is 8 times, and the base here is 3. So 8 times 3 is 24. Let's look at the units. The units here, this is in meters per second, and this is in seconds. So meters per second times seconds is going to give us meters. So this represents how far we've moved. Between 0 and 3 seconds, we've moved 24 meters in the positive direction. So we moved 24 meters, it's positive, so that's forward. So the area of a VT graph gives us the displacement. In this case, it's 24 meters forward. Let's look at this side. This side, for this, we've got a height here of -4 and a base here of 1. So the area here is going to be -4 times 1, which is -4. Units are going to be meters because the area of a velocity time graph is in meters. So we're going to get that we moved 4 meters backward. Now we know, we were told that forward is east, so backward would be west. So this could be written 24 meters east, or should be probably, and this is 4 meters west if you're applying this direction. Now this brings up something that I don't think we've covered in our other graphs, and that is the difference between displacement and distance. These two numbers can be treated differently. The displacement is how far you've moved, and it's a vector quantity. It's where are you in relationship to the start. When you add up displacement, because it's a vector, you must keep the signs. This was positive 24, this was -4. Those are the direction signs. So the displacement is 24 minus 4 equals positive 20 meters, which is 20 meters east. I'm going to use the proper, because we know this is east, I'm not going to use forward and back. Distance is how far you traveled in total. If I go around this room and end up back here, my displacement from start to finish is 0. But I have actually walked a certain amount of distance. So distance is a scalar. You add it up and you ignore the positives and negatives in direction. So the distance is, I walked 24 meters, plus I walked 4 meters. The negative is irrelevant. That is a direction that only goes with vectors, not scalars. So in actual fact, I walked 28 meters. So my displacement, I am 20 meters from where I started. I'm 20 meters forward or 20 meters more east than when I started. How far did I actually walk? My total walking was 28 meters. So this is the difference between distance and displacement. Now what we're going to do is look at a more complicated VT graph, take the area of that, and do another calculation like this, just so that we understand it completely.